Here's problem 3525. A layer of kerosene, index of refraction 1.45, is floating on water, index of refraction 1.33. For what angles of incidence at the kerosene-water interface will light be totally internally reflected within the kerosene? So we have a kerosene-water interface. Let's say N1 is our kerosene 1.45 and N2 is our water 1.33. And like they said, it's going to be reflected within the kerosene. It has to be, because in order to have total internal reflection, we have to go from a higher index to a lower index. So we must start within the kerosene as far as our light is concerned. So we're going to come in at some incident angle. And we view this as if the refracted angle were 9 degrees. In other words, everything is going to end up being totally internally reflected, such that our angle of incidence, theta 1, will equal our angle of reflection. But our angle of refraction is going to be 9 degrees from the normal. Based on this, for total internal reflection, the critical angle, we have Snell's law. N1 sine theta 1 should equal N2 sine theta 2. We want to solve this for theta 1. So theta 1 is the inverse sine of N2 divided by N1 sine theta 2. That's going to be the inverse sine of the water over the kerosene, 1.45 sine, and then our refracted angle is 9 degrees as we're looking at it. Sine of 90 is 1, so it's simply going to be the inverse sine of the lower index over the higher index. 1.33 divided by 1.45, inverse sine, gives me 66.5 degrees. So at 66.5 degrees angle of incidence, that or larger, the light will be totally internally reflected within the kerosene. That will be our critical angle, 66.5 degrees.